me to my first A of A. I'm very happy to present some work with Valentin, which has been kind of a long-term project, but very rewarding. The first thing I want to tell you about is what these things are, up-down chains. The story is actually quite simple. You have a Markov chain, so you have this type of dynamic available. And in each transition in a Markov chain, you can actually decompose them into two smaller transitions, okay? One of these you call an up step, one of these you call a down step. And the terminology is because your up step is going to be making objects larger, the down step makes objects smaller, okay? Of course, you do this in some nice balanced way so that the chain itself actually doesn't disturb the sizes of objects, okay? Examples you can keep in mind are perhaps graphs. So maybe the size of the graph is the number of vertices, right? And so I temporarily have a graph of size n plus 1, but then I go back eventually to a graph of size n. One particular sort of notable example I would like to point out is some work of Petrov, Leonid Petrov, who considers up-down chains on integer partitions. Some details here, but to keep things kind of just at a general level, I'll describe the dynamics in the following way. The down step is just some natural size bias deletion procedure, okay? And the up step is also going to be size biased as well, but some extra model parameters and the fact that this is a growth dynamic means that the more common language to use here is a preferential attachment dynamic, okay? If you're interested in this type of thing, I'll give you some extra sort of detail. You're using a Chinese restaurant dynamic to grow the partition, okay? All right, so that's basically what Petrov's chain is about, but some of the reasons we like its chain, some of the reasons it's interesting, is its connection to some very interesting objects in the literature, one of which are these diffusions of Ethereum curves that are known in population genetics. Okay. Another example, kind of in that same universe, right, are the Poisson-Dirichlet distributions, the things that you've already heard about in this conference, and they show up everywhere in math, it seems, number theory and machine learning and whatever, right? A final kind of connection is to representation theory. Here you can imagine the sort of thing that Greta touched on in her work that shows up in these contexts as well. For the purposes of this talk, and maybe I should say my personal motivation in these objects or in Petrov's chains comes from a slightly different side, and it's the fact that these chains actually form what's called an integrable model. I'll keep things light here. All you need to know is this means that I do have a probabilistic model, as I've described them to you, very natural dynamics, combinatorial dynamics, whatever. But it turns out that there's some algebraic structure underneath everything, okay? And that's what integrability is going to mean, okay? And this is surprising, given what I just described before, right? I just choose some sort of size-biased procedure, a Chinese restaurant dynamic, and voila, there's some nice algebraic structure in the model, right? The other thing that's interesting here, and particularly to me, is the fact that this algebraic structure lets you start talking about scaling limits and convergence arguments, and fairly light convergence arguments. In other words, you can prove convergence of processes with algebraic tools. And for a probabilist, kind of cool, right, that you can do this. All right, some other examples that I want to kind of mention, maybe more quickly, are these works here. Authors are Alexei Borodin, Grigory Yoshansky, another paper by Petrov, and a more recent one that I wrote with Doug Rizzolo. Each of which is interesting in its own right. I wish I could talk about each of them, but what I have the time to talk about here is the big picture that all of these papers have, and it's that they all sort of have the same story, namely, each of them has some natural probabilistic dynamics, but there's some algebraic structure there. And again, that algebraic structure enables convergence arguments. Again, fairly lightly, right? You don't have to work hard. You don't need asymptotic estimates, right? You get very nice formulas. And of course, what is the thing to do here? To ask yourself, why is this happening, right? Where does this algebraic structure come from? How do I get convergence out of this, right? What is some nice framework to understand this? Because we don't really have general tools. You kind of just attack individual models, okay? If you remember the title of my talk, you probably know we were able to make some progress here, right? We're able to sort of talk about up-down chains from a more general level, and in particular, unify these models and Petrov's model from the previous slide. What I'll do for the rest of this talk, I can't tell you what this entire framework is. I'll give you a bit of sort of remarks later. But for now, I can show you what my framework looks like when you specialize it to the context of permutations. And so kind of that's the next portion of this talk. So we'll focus here on up-down chains on permutations. This first thing that you can do is what anyone would do, define some sort of very fixed, some natural objects. First, for the state space, I'll do the obvious thing, right? And take Sn that has a natural notion of size, the obvious notion of size here. And when I want to talk about an upstep, well, to keep things general, I really just need a transition matrix between the right spaces, right? Anything that takes me from Sn to Sn plus 1 will serve as a transition matrix. This is a start, okay? We will eventually make some decisions here. I'll call this thing UN throughout, and the index here is always going to denote where I start, okay? The transition, this upstep, this transition matrix, I'll call it UN, exactly. And indicating kind of the state space that it starts in, okay? I'll do the same thing with a downstep, right? This is the natural thing. I just need a transition matrix moving in the other direction so I can go back to Sn, right? Here, the index that I'll use is n plus 1 to indicate that starts with a large object, in fact, right? And of course, once you've made these two decisions, you have an up-down chain. All you have to do is consider the transition matrix that you get from multiplying the two, okay? Exactly the decomposition that we talked about earlier, okay? So nothing has happened. These are kind of just natural decisions to formalize some of what we've already mentioned. In our context, we actually have to start making some decisions, right? First, we'll always be interested in a family of chains. Again, nothing is still happening, I should say. But now something has happened. For the downstep, we're going to make the decision to focus on a uniform deletion procedure. Restrictive, right? I'm not going to give you any flexibility here, but at the same time, this is a very natural dynamic for permutations, right? Of course. Where you will get some flexibility in our framework is here in the upstep. I'll let you choose your upstep, but I will only impose on you a symmetry condition, which is given by this identity here. What is this saying? Well, on the left, you have this sort of familiar pairing that you've already seen, U and D, which describes the transition matrix of an up-down chain, right? On the other side, you have a DU pairing. Okay, these have the right indices, very nice. On the other side, you have a DU pairing, and this is exactly what you expect. It defines a down-up chain. Very natural object to consider as well, but we focus on the up-down ones, okay? On the far right, you have an identity matrix. It needs to be of the right size, of course, whatever. And these A's that show up are some constants in the unit interval, okay? So the first way you could talk about this condition is just say that the up-down matrix is a convex combination of the identity and the down-up matrix, of course. But probabilistically, what do you want to say? The up-down chain is a lazy version of the down-up chain, okay? Because you just mix with the identity. And this is why I call it a symmetry condition, because the interpretation is that the two chains are the same except for some very simple change in time, okay? So natural condition is what I would like to point out as well, right? And this is the only condition we will need for the moment, okay? Okay, and to talk about kind of our results, etc., I'll remind you a bit of what these things are, pattern densities. If I take a small permutation and a large permutation, a very natural question you could ask is how often do I see the small one and the large one, right? This is what we will mean by sort of density here, and this has already been defined. Just again, a reminder. In the case of these two, the 1-2 permutation showing up in 1-3-2, the density is 2/3. And we can do this calculation sort of quickly. I'll remind you what this looks like. I envision the larger permutation as a diagram. I read it sort of from left to right. This is the graph of the permutation. That's maybe the simplest description there. Height 1, height 3, height 2, etc. What do? I sample pairs uniformly at random, and the first possibility is I get this first pairing here, which is an occurrence of the 1-2 pattern, the 1-2 permutation, because things are increasing left to right? So I have one occurrence in one situation. In the second possibility, another occurrence, things are increasing. But of course, the third possibility is I get a 2-1 pattern, okay? So 2/3 of the time gives me a 2/3 density, okay? All right. Was there a question?
Yes.
Yes.
Your permutation is a row.
Yes.
Permutation is a row. By Petrov, it's a cycle decomposition. And you take a point from the cycle.
Yeah, this is at this point, this framework that we're working on permutations comes a bit different than what Petrov. Petrov started with integer partitions. You can sort of extract permutations if you like from that, but it's not what we're doing. We're working directly with permutations. And here we think of them as functions from n to n. And the diagram then is the graph of that function.
Yes, but you mentioned size bias peak before.
Yes, yes.
That means taking point from the cycle.
Size bias in a different sense. If you like, I can probably elaborate on what that means. It's size bias from you should view it as a Young diagram, and then you make a size bias pick there in some sense. Okay. Clear on this notion here. Okay. All right, so these are bivariate functions. For our framework, we have to fix one of these parameters and use these univariate functions. I call them density functions because I lack imagination, maybe, but these are the objects we are going to need. Okay, we'll fix that first smaller permutation. Okay. So what can we do? Well, the first result that we have are some triangular descriptions. And by this, I mean the following. Take your transition matrix, Tn, any one of them, and there's some natural way to apply them on these pattern density functions from before. You can think a transition matrix acting on a column vector. That's essentially what happens, okay? It turns out that this application happens in a triangular manner. And by this, I mean, if I apply it on d sigma, what do I get? A multiple of d sigma and lower order terms. Lower order here means there's going to be more pattern density functions that show up, a finite linear combination, whatever. And the permutations associated to them will be strictly smaller than sigma. So this is indeed kind of the largest term, right? If you're curious, we know this expansion explicitly, the lower order terms, the constants, but it doesn't help us to see it, at least at this moment, okay? The important thing is that there's some triangular structure, and I use this constant A for the front, or A prime, to just emphasize the connection with the A's that show up in the symmetry condition. Once you know those, you know these, essentially, okay? All right, very nice. What else can I say about this? Well, something I want to point out is the fact that I can vary n and I can vary sigma in this formula, and the result will always hold. And so in particular, more than a sort of triangular decomposition, we have something a bit better, namely that I'm using the same family of functions to triangularize all of the transition matrices, right? And so we have a simultaneous kind of triangularization. This is sort of the integrability that we need. It's a very strong and rich algebraic structure, okay? And in particular, what does this let you do? Well, imagine fixing sigma on the left and letting n move, right? And in particular, letting n go to infinity, right? Then this type of formula starts to allow you to think about limits of the process, right? The limit of those transition matrices. This is a bit imprecise, but it can be made precise, okay? And I'll show you kind of why integrability is doing something nice. Well, on the right-hand side, what is happening when you do this operation? Sigma is fixed, which means the number of terms first is fixed on the right? Moreover, the functions that show up on the right are fixed. The only thing that you have to get a handle on, if you want to take sort of this limit of the chains, is you have to get a handle on those constants in the expansion. You can do that, is the point, right? And so this is kind of the magic. And why, in particular, having a fixed basis, right, throughout n is a big deal. Okay, very nice. So our main result is essentially a rigorous statement that this can happen, right? You can do this. And it's as follows. If I impose some natural conditions, I get the scaling limit. I'll tell you in a bit what those natural conditions sort of are. I'll focus on this though for the moment. The limit object that we get turns out to be Markovian, very nice. And in particular, its state space is going to be this natural space of permutons for the limit. Expected. You can think of them as infinite permutations if you haven't seen them, okay? Another thing I just want to make clear is that this algebraic sort of heuristic I described earlier, you can make completely rigorous, okay? The convergence is relatively easy from the analytic perspective. You don't need fancy inequalities or anything, okay? There's magic is the point, okay? The conditions that we have to use are as follows. First, I need to impose that the initial condition distributions converge. This is standard. So this is why I say this. It's a natural condition, nothing to worry about. And secondly, you have to impose that that your time scaling is going to infinity, which is exactly what time scaling should do. Now, how do you do this, right? That might be something you wonder. Well, it turns out that part of our argument is showing that there is a natural time scaling for these chains. We know exactly how time should scale, but of course, we don't know if it's going to go to infinity as it should. Not in this general sort of setting. Right? And so as long as you can make sure that this does what it's supposed to do, you get the limit for free is the point, right? The strongest condition we've imposed to this point, just to be clear, is our symmetry condition. It's a condition at the discrete level and just on the growth dynamic. Once you have that, you basically get the limit object, right? These conditions are kind of minor. Okay. So yeah, very nice, and of course, as a probabilist, I'm excited that I can get limits kind of relatively easily. Is the point, right? What else can I say? Well, there's some things that we can say about separation distance. I'll kind of do this lightly to give you just the big picture. For this, I'll remind you of some notions. Here, you want to talk about the stationary distributions. I'll call mu n. Of course, this sort of thing varies with n, right? Each up-down chain has its own, right? Okay. What do you want to do with separation distance? Well, this is very similar to what you would do with total variation. You think about the stationary distribution as, right, the goal of the chain, and you want to see how far the chain is from the stationary measure, right? The only difference here that I feel compelled that I have to say, to be clear, is that the separation distance is not a metric, right? So there is something a little different, but philosophically they are the same. You're measuring, right, how far these things are from each other. Okay. In particular, I'm going to be interested in this function here, probably the most precise thing that I'll write down today. So this function depends on n and depends on k. N just indicates the chain that I'm looking at any particular time, right? K indicates how long I'm going to let the chain run. And then, of course, I'm interested in how far the chain will be from stationarity, okay? There's another parameter that matters for a Markov chain, and it's the initial distribution. This, of course, affects, right, how far you are, but that's what the word maximal here is going to refer to, because we can, in fact, consider the worst initial distribution, okay? Which is, yeah, very nice that we can actually say something about this. Clear so far? Okay, so what is the result that we have on separation distance? At least our main result is the following. If I impose some relatively mild conditions, and these I will just hide, but let me know if you want me to say something about them. Again, they are mild, where we essentially expect them to always happen, but maybe there are exceptional cases, so I want to make sure to state that there are conditions. But anyways, under some mild conditions, we can actually get an explicit formula for this thing. Okay. The nice thing here is not seeing exactly what the formula is. The exciting sort of thing here is the fact that you can say something, you can get an identity, right? As opposed to doing asymptotics and that sort of thing, which is the standard thing you would do with separation distance, right? Imposing natural inequalities and so on, okay? So nice that we can get this. This is another sort of testament at the fact that these integrable models are extremely tractable. And this is the point, that you can do so many explicit computations, okay?
Where the worst initial state is and what the state is that achieves the separation?
We know the state, but I mean, we're working in a relatively general framework, right? So I can't say this one precisely, but we can sort of characterize it. We have some way of describing it and identifying it, yeah. Yeah. For permutations, quite often the following would happen. You take extremal permutations, for example, the identity and the anti-identity are generally going to be far away from each other, right? And so this is sort of when, yeah. I think if you start at either one of these, you're likely to get it under some mild conditions. Okay, the final thing that I'll point out is that as is typical of these integrable models, you also have more magic, not just that you get a relatively nice convergence argument, but essentially everything you would like to say about the discrete chains, you can say about the limit as well. For now, I'll limit this to what I've talked about, namely that the two formulas, the triangularity from before, and that this formula for separation distance can be carried into the limit. And some of this is non-trivial, I will also say. It can be done, a bit of work, but we can do it. And in particular, I can measure the separation distance of that permuton process explicitly, again, from a worst case scenario. Which, to my knowledge, and then I will say, I don't work on this enough to know how common this is, but to my knowledge, this is a relatively rare occurrence. So I'm excited about it. If someone knows examples of this type of thing, I would be very happy to hear about it, actually. Okay. All right. So just to summarize very quickly what we've talked about here, so this framework, when I specialize it to permutations, is as follows. Go and find some upsteps that you like, make sure they satisfy the symmetry condition. That's the flexibility I give you. And then check some mild conditions. You can, in general, expect them to hold, but okay, go and check them. Do that and you get this nice convergence. You get a nice permuton process. All sorts of nice properties attached to it, and in particular, it's equipped with a number of nice formulas. In addition, I'll kind of say this in passing. For example, I can talk about the generator of the limiting process, and we can diagonalize it, right? And so you get all sorts of nice properties, even for the limit. And so yeah, and a lot of magic happening. Okay, this is the framework. Again, in the permutation setting, I'll tell you a little bit about what happens in general. Again, too much to talk about, so I'll do this kind of quickly. I have something else to say first, sorry. So a quick example to give you a sense of a permutation model that does fit into our framework, and that these models are not trivial models, right? You have some natural combinatorial models that fit into this. So here's one example. Suppose I give you a permutation, it looks like this, sample some point uniformly at random, and then split it into two, and do this in a very sort of gentle way. You won't disturb any other points. You're going to split very locally so that the new points are close both in the x and y direction. Okay. The only decision to make is whether you get a 1-2 or 2-1 permutation in these new points, and you have a nice parameter to control for this, right? So we have a family of upsteps here, and this fits into our framework. If you want to kill some time on the plane, you can check that this satisfies the symmetry condition. It's a nice thing to check. Yeah. And yeah, this thing is attached to a permuton process is the point. A natural kind of object will come out of this. Okay. All right, so here's, oh yeah, I do also have this, very nice. So this is a picture that I wanted to show more than anything to put a pretty picture in the talk, but this depicts another type of convergence that shows up in our context. Let me know if you're curious about it, we can come back to it. Yeah. Okay, for the general framework, we can talk about other state spaces just to make that absolutely clear. You have a lot of flexibility there. And in fact, you even have quite a bit of flexibility for the downstep. There are conditions to satisfy, of course, you still have to satisfy the symmetry condition, but there is flexibility, to be clear. Perhaps the strongest condition, which I haven't mentioned at the moment, because this always holds when you're working with permutons and permutations, is that you need a natural limiting space. So whatever state space you choose, you need to be able to move into the limit in a natural way. We can talk about precisely what natural means, but you can imagine any normal notion of natural, right? And in addition, we need some nice supply of density functions, just like those pattern density functions in a permutation setting. A nice example here, if you've seen it, well, perhaps the most natural example here might be graphs you might have seen that have natural sort of pattern density functions as well. And then the limiting space is the space of graphons, right? And so that's kind of another natural context you can work in. And okay, the quick comment I want to make there that I skipped is that these additional conditions, those are the analytical conditions, and we know precisely what they are, that you need to make our framework work. In the context of permutations, you don't check these because you can do this ahead of time, right? Permutons have this nice theory around them, and so we already know that everything works out, okay? Okay, yeah, some final remarks here. Okay, first thing, before I conclude this talk, I must acknowledge some work of Fomin that also considers this symmetry condition. So we were not the first, but the intersection there is actually only limited to separation distance. Fomin actually is essentially the one that is devising these general methods for analyzing separation distance of up-down chains, and in particular getting explicit formulas. The difference is that the focus there is more on specific models. And so really what we've done is we've been able to show that this works in general, that's one. And then two, we extend it in various ways, namely extending it into the limit, for example, okay? But yes, Fomin considered this and very much inspired some of the things we do with separation distance. Okay. The other final comment there's a ton of things I could talk about on a number of points here. Some things that, yeah, maybe the last 2 points I'll kind of emphasize. Very nice comments on recursive and uniform models related to this. And then the probabilistic notion of intertwining is a very deeply connected to this framework, actually. So if you have something you want to talk about, yeah, I have a rant about each of these. And that is all. Thank you very much.